Another thing we can do with all of the differential equation solving tricks that we have at this point is solve some geometry problems. So here's a geometry problem that actually comes up in some applied situations, especially involving electromagnetism. So let's say that we have a family of curves. This family of curves happens to be a bunch of ellipses. Which ellipse you get depends on what this constant is. So varying the constant gives you a different ellipse. So right here I have examples of many of these ellipses, and also I have a slider. So if we change C, we can see different values of C give us different ellipses in the family. And the problem that we're going to try to solve is we want to find a family of curves that is everywhere perpendicular to these ellipses. Now what I mean by everywhere perpendicular is wherever our new curves intersect one of these ellipses, it has to be perpendicular to that ellipse. So if a curve goes through this point, then it's going to be something like this. Once it reaches the ellipse next door, it has to be perpendicular to that ellipse, and then the next one, and then the next one, and then the next one. So something like this. Of course, if we draw a curve starting over here, it's going to be perpendicular to that one, and then perpendicular to this one. So you can see traveling from one ellipse to the next tends to curve the graph that we're looking for. You can see since we could start at any point, there are lots of different curves that are perpendicular to all of these ellipses, and so they actually form a whole other family of curves. So that's what I mean by finding a family of curves that's everywhere orthogonal to this family of ellipses. So to solve this problem, what we need to do is figure out some way of characterizing an orthogonal curve. So orthogonal, that's just a fancy word for perpendicular. Right? And for the ellipses, right, the key thing about perpendicular curves is, right, we can characterize being perpendicular in terms of the slope of the curves, because perpendicular curves have negative reciprocal slopes. Negative reciprocal slopes. So we need to, if we can figure out the slopes of all the ellipses, then maybe we can translate that into a family of curves that has the negative reciprocal slopes. Well, for the ellipses, right, we could find the slope of all of the ellipses by calculating dy dx. dy dx, right? Since we have the ellipses as an equation, we could use implicit differentiation. So we could find dy dx with implicit differentiation. Then we could translate that to the perpendicular curves. The slope is going to be the negative reciprocal of whatever we got for the ellipses. So, and the slope will again be some sort of derivative because the curves are graphs in the plane, and so their slope is the derivative. So what we expect to have happen is we'll find dy dx, we'll take a negative reciprocal, that will give us a differential equation, and then we can solve that differential equation to find the perpendicular curves. So that's a plan. Let's see how this plan works out. So we're going to start with our equation for the ellipses. X squared over 4 plus y squared equals some constant. Now remember, to do implicit differentiation, what you do is just take the derivative of both sides with respect to your independent variable, which is x. On the left-hand side, derivative of x squared over 4 is x over 2. Okay, now the derivative of y squared, remember, y is secretly a function of x. And so we have to do the chain rule here. There's an inside and an outside. The outside part is the squaring, so the derivative of a square is 2 times the inside to the first power, but then we have to multiply by the derivative of the inside. The inside is y, so the derivative of y is dy dx. Then on the right-hand side, the derivative of c, well, remember, c is a constant, and so its derivative is 0. Okay, now we can solve this equation for dy dx. Just move the x over 2 to the right, 2y dy dx equals negative x over 2. And then to finish solving for dy dx, divide by 2y. So dy dx equals minus x over 4y. Okay, and this is for the ellipses. Now remember, our idea was to switch to the perpendicular curves make the slope, well, dy dx is the slope of the perpendicular curves. We need the negative reciprocal of the slopes for the ellipses. So we just need to drop the minus sign and turn this fraction over. So 4y over x. All right. Now, see, we did get a differential equation for the perpendicular curves. And we can solve this differential equation. It looks like it's separable. So let's separate. We get dy over y equals 4 over x dx. Then integrate both sides. On the left-hand side, we get natural log absolute value of y. On the right-hand side, we get 4 times natural log absolute value of x. Okay. We're going to exponentiate, but before we do that, I want to move this 4 inside the log. So natural log absolute value of y. Oh, I forgot my constant. I need plus a constant. Okay, equals natural log x to the 4th. Now that I have x to the 4th power, I don't need the absolute value because x to the absolute value of x to the 4th is the same thing as x to the 4th. Plus a constant. Now we can exponentiate. We get absolute value of y is equal to e to the natural log x to the 4th plus c. As usual, we're going to split this up. So e to the natural log x to the 4th times e to the c, but we're going to rename e to the c a. So absolute value of y is equal to, so e to the natural log x to the 4th, that's just x to the 4th. And a can be any constant. In principle, a has to be positive because it's e to the c, but if a has to be positive when we have the absolute value of y, we can remove the absolute value by just removing this condition that a has to be positive. And so we get y equals a times x to the 4th. So this is our family of perpendicular curves. To check that this actually works, let's graph these things. So let's see, we need an arbitrary constant, a, so let's make it 1 to begin with. And let's just graph y equals a times x to the 4th. Okay, now remember what we're looking for here is that every place this graph intersects these ellipses, it's perpendicular. So if you look closely at all of these intersection points, those do all look perpendicular. In fact, even as we change the value of a, so that our quartic function is changing here, all of these quartics are perpendicular to all of these ellipses. Even when a is small and the quartic is very wide, like that, it's still perpendicular everywhere. And even when a is negative, it flips down to the negative half plane. All of these are also perpendicular to all of those ellipses. So we succeeded in finding a perpendicular family of curves. In electromagnetism, this is a nice thing to be able to do because one family of curves might be your electric equipotentials, in which case the field lines point along the perpendicular family of curves. So in those situations, it's nice to be able to switch from one to the other.